Chapter 14, Linear Regression. This is a continuation of the previous video produced for correlation. So again, regression is used to primarily make predictions given the relationship between two variables. So Pearson correlation measures a linear relationship between two variables, and we've learned how to calculate that using the SP and SS for S and SS for Y calculations. In the next figure, we'll see how the linear regression makes the relationship more obvious. The line through the data makes the relationship easier to see and understand, as well as show the central tendency. So chapter 3 was central tendency. Regression, from a psychology perspective, refers to the backward movement to, let's say, a childhood state. So in statistics, it means the backward movement towards the mean of the distribution. So we can think of the regression line as representing the average tendency of this relationship. So again, the average tendency of how these two variables move together. And we refer to that as the central tendency. So the mean is thought of as the default. And we can again use this regression equation to make predictions. So you can think of the regression analysis as precisely defining the line that visually illustrates the relationship between the two variables. So here's an example of a regression line with two variables that are very strongly positively correlated, and we know here visually it's positive because we have a positive slope, upward slope of the line, and we would consider this to be a strong relationship because of the fact that these data point coordinates, the coordinates are closely related to that regression line. So this is visually showing us the relationship between SAT scores and GPA. So again, other things that we'll discuss in a moment is the slope of the line and how to calculate that, as well as the y-intercept and how we can use those two variables, which are then considered constants and never changing, and use that for predicting a value of y given a value for x. So this is the basic linear equation. I'm sure you've seen it in previous classes, perhaps with the use of different variable labels. But the equation for linear line is y is equal to bx plus a. And x and y are variables, so we'll be using this equation to make predictions of y given a value for x. And then a and b are fixed constants, or in this case we refer to them as correlation coefficients, where b is equal to or represents the slope of the line, and we understand slope to represent the amount of change in y with each 1 unit change in x. So I'm sure you've heard of the phrase rise over run. So again, it's the amount of change in y with each unit change in x. And a represents the y-intercept. And we understand that to be defined as the value of y when x is equal to 0. So again, once we say those are fixed constants, the correlation coefficients, because once we solve for the y-intercept and the slope, so a and b in this equation, we can make predictions of y all day long given the value of x. In other words, we can say if x is equal to 1, then y, is equal to, and then we would again use our equation, y is equal to slope, in this case x equal to 1 minus our intercept. So once we solve for the slope and intercept, we can make predictions again, but we're confined to the original range of the data that was collected to produce our correlation coefficient, our Pearson R value. 14.4, the figure in the textbook, is a good illustration of the concepts of y-intercept and slope. So the example pertains to your total cost to have a membership at a video store. A somewhat archaic example nowadays. Video stores aren't really around as much anymore with other technologies available such as Netflix and Amazon Prime and others. Regardless, we have this example that says that the video store charges $5. So $5 membership. And they charge $2 per video. So we can think of that $5 as the y-intercept, because if we never rent any videos, if x, so in other words, if x were to equal 0, we don't rent any videos, our total cost for the year would be $5. Because again, that's the total cost, which includes membership only. So again, if we think of our equation, y is equal to bx plus a. So again, our total cost is the y value that we're trying to solve for. And the $2 represents the slope, because it's the amount of change in y for every unit change in x. So every time I rent a video, so I rent one video, right, the value of y changes by $2. I rent another video, and then the value of y changes by 2. So in this case, we would understand a to equal 5, which is the y-intercept, and b is equal to 2. So every time we rent a video, it's an additional $2. Right, so let's use those values in our equation, and here where we say that if we rent 3 videos, right, 3 videos, what will be our total cost? So y is equal to 2 times x, which is equal to 3, plus our $5 yearly membership. So y is equal to 6 plus 5, and we get 11. So again, if we rent 3 videos, our total cost will be $11. This example of 8, we can also use that. Y is equal to, so the slope, 2, times how many videos I rent, 8, plus my yearly membership of $5. So y is equal to 16 plus 5 is equal to 21. So we see where those intersect. So again, this is a great example to understand that concept of y-intercept, the value of y when x equals 0. I rent 0 videos, so my total cost is $5, the basic membership. And then slope, the amount of change in y for each unit change in x. So every time I rent a video, the slope increases, right, or the value of y, I should say, increases by 2 because it's $2 per video. Okay, so regression is considered a method of finding an equation that describes the best fitting line for a set of data. And we define best fitting as the straight line where we minimize the error or between the prediction and the actual. So we consider y is the actual value and y hat equals the predicted. So given our relationship between two variables, we can again calculate our R statistic and then solve for slope and intercept and then make predictions for X and then create a regression line. The regression line again is going to minimize the error between the actual and the predicted value. Please understand that the stronger the correlation, the more accurate our predictions. The weaker the relationship, the less accurate our prediction. Okay, so y hat, as I just indicated, is the value of y that's predicted by the regression equation for each value of x given. And then y minus y hat is the distance each data point is from the regression line, we refer to that as the error of prediction. And then the regression procedure produces a line that minimizes the total squared error. So we're going to calculate a value that measures the distance between the actual and the predicted, and we're going to square that and take the summation, and we refer to that as the error, the sum of all squared error values. And we want to minimize that so that we produce the best regression line. So this method is referred to as the least squared error solution. So here's an example, visual example of this idea of the error. So you see the blue line represents the regression equation that was calculated using our correlation coefficient, solving for the y-intercept and the slope of the line. And the data points, the coordinates, show the actual data that was calculated. And the distance between the data point line and these coordinates represents the error. As we see here, the distance between the actual and the predicted. And again, we want to minimize that distance. The goal of regression is to find the equation for the line that minimizes these distances, but also another requirement is that on that regression line, we should include the mean of x and the mean of y. So that's another criteria for calculating our regression line. If we think back to the balance point of the mean when we were looking at the teeter-totter and how the mean represented the equal distance from the center, this is similar that if we were to calculate the difference, so this value here that's shown, the distance between the actual and the predicted, and any value below the regression line would be considered negative, and values that are represented above the regression line are positive. All of those would cancel each other out. So again, earlier I stated that the regression line is a visual interpretation of the central tendency, the mean, the average movement of these two variables. And so if we take that distance, anything below the regression line would be considered negative, anything above would be considered positive. And we would take the summation of all those distances or deviations or errors, they would cancel each other out. So when we're making predictions, the regression line now reads as y hat. Y hat is the predicted value of y, is equal to the slope multiplied by the given value of x added to the intercept. So the slope of the line, again, b, can be calculated using this equation. We're given both, but I do not recommend using this one. Calculating the slope using your sum of products of deviations over the sum of squared deviations for your x distribution is the ideal equation to utilize. Using the standard deviation of your two distributions just takes an additional step, if not two steps, for each distribution. So again, I recommend that you use the first equation to solve for the slope. And again, the slope is representative of the amount of change in y with each unit change in x. And then our line goes through the mean of x and mean of y. So I recently mentioned that that's another criteria, that the regression line includes the average score for our x distribution in conjunction with the average score of our y distribution. And a, the y-intercept, is equal to the mean of our y distribution minus the product of the slope multiplied by the mean of x. And again, the y-intercept is representative of the value of y when x is equal to 0. Again, as stated before, once the correlation coefficients have been calculated, the slope and the intercept, we can make predictions of x, again, limited to the original range of data points that we had collected to compute our R statistic. And here we have our regression equation, and we can understand from this equation that the slope is equal to positive 2, and we see that visually. There's a positive slope upward trend of this relationship, and our y-intercept is equal to negative 1, which is again indicating the value of y when x equals 0. It's not demonstrated on here, but again, if we were to take this line further down, right, it would cross the y-intercept at negative 1. So if x is equal to 0, y would equal negative 1. And again, the slope is the change in y with every 1 unit change in x. So notice here the value of the mean of x and the mean of y. So if we were to use our equation and said that if x is equal to 4, y hat would equal 2 times x, which is 4, minus our intercept, which is 1. Therefore, y hat is equal to 8 minus 1, which is equal to 7. So we see that that point is included in our regression line. So again, the correlation coefficients of the slope and the intercept become constants, and we can keep changing the value of x to predict the value for y. Standard error of the estimate. And this represents the average distance between the actual and predicted value of y. So the regression equation makes a prediction. Obviously, the prediction is more accurate the stronger the relationship. The predictions are less accurate when the correlation between two variables is weaker. So the precision of the estimate is measured by the standard error of the estimate. So again, it's calculating on average, how off or how much error is expected in this prediction, and it's grounded in the original correlation or relationship between the two variables. So here I have the three different equations you'll see in calculating the standard error of the estimate. The SS residual is referred to as the error or unpredicted change or variance in a variable, and we can calculate it by taking the sum of all the error that's been squared and divided by the degrees of freedom and take the square root. It could also be calculated by taking 1 minus our correlation coefficient squared, or the correlation of determination, and divide that by n minus 2. Excuse me, I should make this a little clearer here. This goes all the way through. So we take 1 minus the coefficient determination multiplied by the SS of y divided by n minus 2 and take the square root of that. So there are different methods by which we can calculate the standard error of the estimate, but essentially the standard error of the estimate is representing the average of error that we would anticipate given the original correlation or relationship between two variables. In these two examples, in the first one, it's a perfect relationship. So we would say R is equal to positive 1. And again, the slope is equal to positive 2, and y-intercept, actually I'll just, is A representing the y-intercept is equal to negative 1. So again, the value of y when x is equal to 0, and so that would be negative 1 down here. If we move up 2 from negative 1, that puts us at 1, and we know that if x is equal to 1, then y is equal to 1 because of the relationship, and we know exactly how the y variable is going to change if r is equal to positive 1. So we see exactly the distance between the two. So if we move to 2, y is equal to 3. If we move to 3, y is equal to 5. And again, there's no error. We know exactly what y is equal to when r is equal to 1. However, in this example, r is equal to positive 0.84. It comes from a previous example in the text. And I illustrated this before. Again, the slope and the intercept are the same as the previous graph above. But now, since r is not perfect, we see some residual or difference between the prediction and the actual. Right? And so we recognize that there are errors in our predictions simply because this does not equal a perfect one, negative or positive one. So the relationship between correlation and standard error, as I indicated earlier, the accuracy of our predictions are going to be a function of how strongly or weakly correlated two variables are. So as r goes from 0 to 1, and it could be negative 1, the standard error of the estimate decreases to 0. So again, the stronger the relationship, the smaller the standard error of estimate, which makes sense because the stronger the relationship, the less error in our prediction. So the average difference between our predicted value and our actual value decreases. And we have a new statistic referred to as SS regression. And this is an illustration of how variables move together, right? How they're changing together as a result of the relationship. And we refer to that as the predicted variability in y. And the unpredicted variability of y is referred to as the SS residual. Residual, again, referring to the error between our actual and predicted value. So we can understand this as how variables move independently. So aside from the relationship, we do see variation in our y-scores due to chance and random factors. And so the movement is not attributed to their relationship. And then here at the bottom, we have our estimated standard error or a standard error of the estimate based on our correlation coefficient. So again, the stronger the variables are correlated, the more accurate our predictions, and the lower the standard error of the estimate. So in order to test the regression line for significance, to see if the regression line is a good way to make predictions given the original correlation, we can use the analysis of variance, similar to what we did in Chapter 12. In Chapter 12, we looked at a F ratio that assessed the variance between groups over the variance within groups. So variance within groups explained by random unsystematic factors, variance between explained by unsystematic factors in addition to treatment effect. And we're going to do a similar analysis using an F ratio. So the F ratio can be explained as a ratio of variance due to relationship over variance due to other factors. So again, that residual, the difference between the actual and the predicted value, is the error, and that movement or variation is explained by other factors. And so the variance due to the relationship is what is grounded in our correlation coefficient. So our test of significance is going to be based on a null hypothesis that says the slope of the regression line, or beta, is equal to 0, so there's no relationship. So visually that means if we have our y and our x, right, the slope would be equal to 0. R is equal to 0. There's no relationship. In other words, every time the value of x changes, right, the prediction of y will always be the mean of that distribution because there's no relationship between the two. So the alternative research hypothesis states that the slope of the regression line is not equal to 0. That it would either be a positive or negative slope, but depending on the relationship, but it will not equal 0. So the structure of our F statistic down here is similar to what we saw in our analysis of variance. It's an MS over its corresponding degrees of freedom. So again, the SS regression expresses variance as a result of relationship. And MS residual represents variance due to other factors. And they have their own individual degrees of freedom. So we'll see that in the next slide, but for now, degrees of freedom regression is equal to 1, and degrees of freedom residual is equal to n minus 2. So similar to analysis of variance, once we get our MS regression, MS residual, the F statistic is the ratio between those two. Again, the numerator expressing the variance due to the relationship, and then over, as we just indicated, variance due to other factors. And once we calculate our F ratio, it'll be a process of comparing that F statistic to a critical F using the degrees of freedom regression and degrees of freedom residual to enter our F table and find our critical F and make the comparison. If our F ratio calculated is larger than the critical F, we get to reject the null hypothesis. And if it isn't, then we fail to reject the null hypothesis. And finally, SSY represents the variability of Y, and it's explained by two things, the variability due to the relationship and the variability due to other factors. And the degrees of freedom for Y is n minus 1, and we see that that's a function of degrees of freedom for regression is equal to 1. And when we're working with two variables, degrees of freedom of the residual is equal to n minus 2. So again, focusing on over here, the variability of Y is an expression of the change due to the relationship and the change due to other factors.